Hello everyone, I am Kailas Prasad, PhD scholar from Nano Electronics Devices and Circuit Lab, Department of Electrical Engineering, IIT Gandhinagar. So I'm re-recording this, the first part of this lecture. Actually, the first part of this recording has failed. So I'll be discussing till the fourth question here again, and I will attaching this with the existing video lecture, and I'll be uploading that. So this the we are here for the tutorial session for design and analysis of VLSI subsystem. The course has been taught by Professor Madhav Rao, and this session happens every Tuesday from 7 p.m. to 9 p.m. So in the live session 8, actually we are trying to discuss the questions of week 9 and week 10. Okay, so in the next session we'll be discussing about week 11. So we will start. Just a quick overview of what we have done till now. So the course is VLSI design. So initially we have started with the transistors, right? The CMOS logic and the current model we have seen that, okay, how the current flows and all. Then we have designed a very basic circuit that is called as inverter. We have analyzed the characteristics of inverter, both in terms of area, power. Along with that, we have also discussed about noise margin and the delay of the inverter. Then we have discussed about RC delay, where we have discussed about Elmore delay model, the pi delay model. Along with that, we have also discussed about the delay optimization using logical effort. So that was which we have been discussing till week 5. After that, we have started with combinational logic families, right? So in the combinational logic families, we have discussed combinational circuits like the AOI gates, the OAI gates. Along with that, the pseudo and MOS, and along with that, we also discussed about the dynamic logics. Then we have moved to the back end of the design. So that was the front end, where we have been discussing about the layouts. In the layouts, I have actually taken a detailed tutorial where I have actually shown you the CMOS fabrication process flow, right? So if you have not seen that lecture, it is extremely important. You go back and you see the lecture on the layouts which I've shown you guys, right? That lecture becomes very important, because when we talk about the layout, right, you should understand that when I'm saying that, okay, this is the diffusion layer where it will be kept, or if this is the contact in the 3D view, how it will be seen. Okay, so that's the reason that lecture becomes very important. Then we have learned about the stick diagram, right, by which you can effectively make the standard cell layout. Okay, we have followed up this discussion with the interconnects, right? So in the week 7 and week 8, we have actually discussed about interconnects. And in the last lecture, we have been discussing about power. So we have discussed two questions on power. Here also, we will be continuing that part. So let me first go to the previous lecture. Okay. So these were the two questions. The first question, okay, so I will just remove this part. Okay. So the question here says that a chip composed of random logic has an activity factor of zero point 0.1. Okay, so the first thing that you have to realize in the power equation is what is the activity factor. So let me write the power equation for you. So P equal to alpha C VDD square into F, right? So this is my equation. So the equation of dynamic power. Okay, so wherever I'm writing this equation, please note that this is the equation of dynamic power. Okay, in today's lecture, we also will be discussing about the static power and the static current, right? But currently we are actually discussing about the dynamic power. In the dynamic power, I have discussed about what is the contribution of each of these component, right? And why this each of these component contributes towards the power, right? So activity factor means, right, what is the probability of switching of any gates, right? So if there is any input, right, what is the probability that it will switch? Okay, so the more the switching will be there, the more the dynamic power. Okay, so that's the reason power is directly proportional to the activity factor. The second component is the capacitor, right? So what happens that whenever your gate switches, it takes some time to switch, right? And why it is taking some time to switch? Because of the intrinsic or parasitic capacitance which are associated with the transistor. Okay, so the more the capacitance, the more the slew will be, right? So it will take more time to switch. And if it is taking more time to switch, it means for more time your PMOS and NMOS are actually turned on. So more current will flow, more power consumption will be there, right? So that's the second point. Okay, second point about capacitor. The third point is the VDD, right? So VDD is the current is actually directly proportional to the square of the VDD. Okay, I equal to mu NCF W by L VGS minus VTH whole square, right? So if your VDD changes, current changes in the square, right? So that's the reason power also changes in terms of square, right? So VDD becomes extremely crucial while talking about dynamic power. That is the reason when we are trying to go from say 90 nanometer to 65 nanometer to 28 nanometer or 7 nanometer, right? We are trying to reduce the VDD because VDD reduction actually reduces the power in the square law, right? But in the advanced technology, not due to the threshold voltage being not being scaled, right? The VDD scaling has actually been stopped or it has slowed down. Okay. Apart from that, the last thing is the frequency. The higher the frequency, higher the dynamic power consumption, right? So that is the thing. So in the question, it has been given over here is that our alpha is equal to zero point 0.1. Okay. The other thing which is given is that you are using a standard cell process with an average switching capacitance of 450 picofarad per millimeter square. Okay. So C switching, okay, that is average is 450 picofarad per millimeter square. Okay. Now the question here is estimate the dynamic power consumption, right? So we have written the formula of dynamic power, right? Please understand that dynamic power is the power it when consumed when there is a switching, right? The switching can be of three things. Okay, the first is your inputs, the second is your outputs, and the third is your internal nodes. Okay, if any of these three switches, right, there will be dynamic power consumption. Okay, and so whenever there will be a switching, the current will flow, right? The internal capacitance or input or output capacitance will either charge or discharge. At that time your CMOS will be turned on, the NMOS and the PMOS will be turned on at the same time, right? There will be power consumption. So you have to understand that. Okay, the static power consumption is when there is no switching. Okay, when your device or the circuit is at the static state, right? You have provided a fixed input and it is a static state. Whatever the leakage that is going on contributes to the static power. Okay, the question given over here is that estimate the dynamic power consumption of your chip if it is has 70 millimeter square of area. Okay, so we can actually calculate the actual switching of C actual switching, right? So this will be my 450 in picofarad uh, per millimeter square multiplied by 70 millimeter square, right? So whatever the result, it will give me the exact capacitance. Okay, the frequency given over here is 450 megahertz. Okay, and the VDD is zero point 0.9 volt. Okay, so the question is very simple. Okay, you just have to calculate the dynamic power. Okay, so to calculate dynamic power, you put all the values alpha into C is 450 multiplied by 10 to the power minus 12 multiplied by 70. Okay, and then VDD is zero point 0.9 square, then it is multiplied by 450 into 10 to the power minus 6. Okay, and if you will calculate this, you will actually get 1.148 watt. Okay, I have calculated that, but the final answer will be 1.148 watt. Okay, so this is how the dynamic power is being calculated. If you are given with all the parameters, you can easily calculate the dynamic power. Okay, but apart from that, whatever I have discussed, the important points, right, those are the very important points. The calculation is not important, rather the concept behind the calculation becomes important. Okay, if you are reading a formula, you should understand that each of this component, how each of this component is contributing to the y, right? So if these are my function of x, right, how each of this component is contributing to the dynamic power. Okay, now moving to the second part or the question number 8. Okay, so this question has also been discussed in the previous classes. I will just repeat for the completion sake. Okay, the question given over here is the switching probability of output y in a 3-input NAND gate, right, can be expressed as. So you just have to calculate the switching activity, what is we call as alpha, right? Now how do we calculate the switching activity? What you have to do, you have to make the truth table. So this is an AND gate. So what I will do, I will make a truth table of an AND gate. Okay, so if this is my A, B, and C, and this is Y, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And this is a NAND gate, so it is an opposite of AND gate. So all the cases, for all the cases, it will be 1, right? And for only one case, it will be 0. Okay, so you see, if I calculate the probability for all the cases, it is 1, right? And there is only one case, it is 0, so it will be 1 minus, right, whatever the probability of this, right? So this will be all ones, so it is 1 minus PA, PB, and PC, right? But if you see this particular equation, it is not there in any of the option. So what I will do is I will try to make apply a De Morgan's law, right? And let's see if this is available or not, right? If I apply De Morgan's, it will be 1 minus PA bar plus PB bar plus PC bar, okay, to the bar. So it will be this option which is correct, right? So this is how you calculate the switching activity, right? If I ask you a question that which is the gate which has highest switching activity, it means which gate is bound to consume highest power, the answer will be an inverter, right? Because its switching activity is zero point 0.5, either it will be 1 or 0, right? Every time the input changes, it will switch, the output will switch, right? So it has a zero point 0.5, so that's the highest consuming energy. So whenever you design circuit, you want that, okay, as less as inverter chain or inverters are there in your circuit, right? Otherwise there will be very high dynamic power consumption in your circuit, right? So this point you have to keep in mind while designing the circuit. Now coming back to this lecture, okay, so let's move to the first question. Okay, so what we have done as of now, we have calculated power. Okay, power is alpha C VDD square F. Okay, then we have also calculate the alpha of one of the question, right? Now this question states over here is a clock signal with a period t equal to 10 nano. Okay, so time period is 10 nanosecond. Okay, with an amplitude VDD is equal to 1.2 volt. Okay, then what has been given over here is yeah, VDD is 1.2, capacitance is 1 nanofarad, C is 1 nanofarad. Okay, so the question is, what is the cumulative energy supplied by power supply to inverter at the end of every clock cycle, right? What is the cumulative energy um, that has to be asked, right, after every 10 nanosecond? Please understand that energy is not a function of time, right? Power is a function of frequency, but energy is not. Okay, so energy is CVDD square. Okay, so energy here will be CVDD square. Okay, so this is actually not a function of time. So when we calculate for say 1 times 10, right, for say 10 nanosecond, we just have to add it up to get for 20 nanosecond and to get for 30 nanosecond. Okay, so if we calculate this, so C is 1 nano. Okay, then VDD square is 1.2 square. Okay, so this will be 1.44 into 10 to the power minus 9 joule, right? So this is 1.44 nanojoule. Okay, so how many questions we will have this answer? There is only one, right? So if we want to calculate at 20 nanosecond, you add it two times. Okay, 1.44 plus 1.44, this will be 2.88, right? So this is the answer. So the cumulative energy it has asked. So for after one cycle, it will be 1.44. After two cycle, it will be 2.88. After three cycle, it will be 1.44 multiplied by 3, that is 4.32. Then after four cycle, it will be 1.44 multiplied by 4, which will be 5.76. Okay, so this is how this question has to be done. Now, moving to the next question. The question states over here that the static power dissipation is not due to. Okay, so I have discussed about the dynamic power in the previous question, right? Here, what we have to discuss is about which of this region is not due to the static power. right? Or which of this reason doesn't contribute to static power. Okay, so what I have said about the dynamic power, whenever there is a switching, right, whenever there is a so there is an a input, okay, this input goes from 0 to 1, right, at this instant, right, if output goes from 1 to 0, right, this instance will be the where the dynamic power consumption happens, right? And why do at this point dynamic power consumption happens? Because at this point both NMOS and PMOS are on, right, partially on, right, and a current flows between VDD and ground. Okay, so this contributes to dynamic power, right? And if you see the question over here, the fourth option, the short circuit current, while both PMOS and NMOS are partially on, actually contributes to the dynamic power. Okay, so that's the reason for this question. The answer here is the short circuit current is not contributing the leakage, right? The leakage happens first due to subthreshold leakage, right? So for static power, the first thing is subthreshold leakage, right? So let me explain you why subthreshold leakage, or what do you mean by subthreshold leakage. So ideally what we consider that our transistor should be switched, right? It should be either off or it should be either on, right? But what happens that our transistors are not ideal switch, even though, right, when you remove the, so when you give input 0 to the gate, right, there are some minority charge carrier which flows because of the reverse bias, right? So that's the reason we have subthreshold leakage, right? And lower the VT, right, more the subthreshold leakage, and that you have to understand. The second is the junction leakage from source to drain. So again, this all these junctions are reverse bias, and the reverse bias leakage current flows. Okay, and the third one is gate leakage. So what happens when we go from higher to lower technology nodes? So this is true till I think 45 nanometer, right? Uh, the gate is becoming very thin, right? The oxide is becoming very thin, right? Ideally, it is an insulator, right? If you apply a voltage over the gate, one side of the gate, the charge will be accumulated to the other side. There won't be direct connection between them. Okay, but what happened due to extreme thin oxide, right? It has started tunneling through the gate. Okay, so that we considered as gate leakage. So to overcome that, to overcome or to reduce the gate leakage to a gate extent, people have used, or this is Intel was the first one to be using, is they used high K dielectrics. Okay, high K dielectric means that the oxide thickness, oxide will having high K value, right? High dielectric value, right? So even if you increase the thickness of the oxide, you can still get the same capacitance, right? The capacitance is directly proportional to the gate control, right? And if the you have a larger width of or larger thickness of the high K dielectric, so your the gate tunneling won't occur. Okay, so this is actually employed today also in all the technologies to prevent the gate tunneling. So this is the thing. Now, so yeah, so the three reasons for which, because of which the static power dissipation happens, is subthreshold leakage, the reverse bias junction leakage of the source drain and diffusion, and then the gate leakage. Okay, so what are the importance of both dynamic and static power, right? So for static power, so why static power is important, and why do are we trying to calculate, or we are trying to study the static power? Okay, so that's an important question to ask. So the thing is, if you have a mobile or a laptop, right, which is battery operated, right, and if you just keep your mobile and laptop in the idle position, right, what happens that if you see your mobile or laptop after say one day or day or two, right, the battery goes down, right? Ideally it should not happen. Okay, but because of this leakage, the static power, it happens, right? And you want that the static power should be as low as possible, such that it will increase the battery lifetime. That's the first point. Okay, the second point is, whenever you're say you're trying to play a game, video game like PUBG and all, and or Counter Strike, right, you are actually making lot of read write from the memories, right? Lot of switching is happening, and at that time whatever power will be consumed, that will be dynamic power. And that's, you might have observed that whenever you play game, right, your battery drain very fast, right? And the reason is behind it, right? Whenever there is a switching, the power consumption will be there. What do we want is that we also want that this dynamic power consumption should be also low, right? Even though we play games, right, our laptop should last for say 10 hours, right? Our goal is at least it should last for 1 day, right? We are not very near to that goal, but in future we will be, right? We are trying to build energy efficient system. Okay, so moving to the third part, right? So I have shown you the equation of the dynamic power, right? Now we'll be discussing about the leakage, okay, the static power. So the question states over there that you can choose a MOSFET from a different sets of MOSFET with varying VT0 from 0.3, 0.26 and 0.21. Okay. Assuming the subthreshold slope is equal to 105 millivolt per decade and DIBL coefficient is 98 millivolt per volt, right? And the same body effect coefficient of 0.067 for all the MOSFET, how much instantaneous power due to subthreshold leakage can be saved choosing the lowest static power MOSFET as compared to the highest static power MOSFET from all set. Right? Consider that there is a single NMOS with VDD is equal to 1 volt, VG equal to 0 volt, and use this equation to calculate the static leakage current. And it has given that N is 1.3, VT is equal to 26 millivolt. Right. So this is not a difficult question to solve. You just have to provide appropriate parameter. But before that, right, what you have to do is you have to compare the lowest static power MOSFET and the highest static power MOSFET, right? So see, VDD is fixed. So if we compare the current, right, we are actually comparing the power itself. Okay, so even if we can find out the current at say a high static power zone and at the lowest static power zone, and if we take the ratio, it will be our answer. Okay. Now the question is, when does the lowest static power will happen, right? So we have a three flavors of MOSFETs available over here with zero point 0.3 volt, 0.26 volt, and 0.21 volt. Okay, so these three flavors of MOSFET has three different VTs, right? So I have already said, right, if you reduce the VT, right, you can see that if you reduce the VT, the current, the static power increases, right, the static current increases. So that is the highest power static power zone, right, the lowest VT, and the highest VT will be the lowest static power zone. So I want to discuss that there are multiple VT transistors which are available, just like RVT, LVT, okay, HVT, and then we have ultra LVT, right, extreme ultra LVT, similarly ultra HVT, right, then extreme ultra HVT, right? So these are the regular VT transistors, but the foundry, whatever foundry you are working with, they provide these many flavors of transistors, right? Now as a designer, it is your choice to choose whatever transistor you want, right? But what you have to understand is what are the properties of each of these transistors. See, as we are moving down, the VT is decreasing. Okay, if VT is decreasing, it means the current will increase, right? Both the static and the dynamic current will increase, right? So the on current, if on current increases, it will be more fast, right? The switching will be more fast. So that is the advantages. However, as we move from up to down, right, your VT is decreasing, so static current is also increasing. It means that the power consumption will also be high, will also be high. Right, so that you have to take care that okay, what flavor you want to choose. If you want to say have an ultra low power device, right, just like in your the smart watches, like in the pacemaker, there you don't want that your circuit should work at say 1 gigahertz, right? What do you want is your circuit or your whatever the smartwatch you're wearing should actually last for say 10 days. The pacemaker should last for years, right? So for those application, you will choose a transistor with extremely low leakage, right? So the ideal choice will be extreme ultra high VT. But if you're talking about the supercomputers, right, the servers, the Amazon and Google, the servers, if you're talking about there, you want that okay, the output should come as fast as possible, right? There, whenever you want to use any transistor, you'll use LVT, ultra low VT, or extreme ultra low VT transistor, depending upon whatever the power budget you have. Okay, so this you have to take care. So for our question, if we come back for VTH is equal to zero point 0.3, right? If I calculate whatever current will be, right, you just have to put the formula, and if I put the formula, the I sub will be IDS 0, multiplied by this I have already calculated. You just put all the variables and you just calculate, right? This will be into 10 to the power minus 3, right? And at VTH is equal to 0.21, the I sub will be IDS0 multiplied by 36.38 into 10 to the power minus 3, right? So what do you want? You want the percentage saving of having say low VT as compared to HVT, right? So it will be how much? You just take the ratio, or so by subtract and take the ratio. So percentage saving will be 36.38, right? 10 to the power minus 3 I'm removing, right, because it will be cut, subtracting from 2.5 divided by 36.38. Okay, and if you get this number will be around 93, right? So please understand that by choosing a transistor of zero point 0.3 volt as compared to 0.21 volt has reduced your power consumption by 93%, right? So as a designer it becomes extremely important to choose, right, which transistor you want to have, right? So this has reduced. There will be obviously penalty in terms of on current, so that's a separate concern. But if you are actually looking for a low power application, see how important your threshold voltage is. Okay, so this is the question number 3. So up to this actually the recording was not there. Okay, so so in the next part, I am just clubbing the recording, and we have discussed about the question 4. I will just read the question for you. So you are considering lowering VDD to try to save the power in a static CMOS gate while also scaling VT proportionally to maintain the performance. Okay, how does it affect the static power and the dynamic power consumption? Now, if you actually what you are trying to do is, if you are not reducing VDD, okay, if you are increasing the VDD, the dynamic power will increase, right? So if you reduce the VDD, dynamic power reduces. If you increase the VDD, the dynamic power will increase. Okay, now the second point over here is if you reduce the VT, what will happen? So if you reduce the VT, the static power increases, right? So in the scaling you are reducing the VDD, right? You're reducing the VT also because you want the same ion. Okay, although your dynamic power is reducing, the static power increases. Okay, so in that case what happens, the dynamic power is actually reducing, not this one. The static power is actually increasing, right? So this will be the answer to this question, right? So there is a trade-off. Okay, now I will move to the next question. The node voltage are static with respect to time in which of the latch design? Anybody knows this answer? So if you change the time, the node voltage will remain the same. So answer over here will be, there are only two latches, right? CMOS and the jam latch. Okay, in this latch only there is actually a feedback. Okay, there is a feedback. Okay, whenever there is a feedback, then your node voltage will not change with time. Okay, so simple cross couple feedback can be like this, right? And if you put transmission gates over here, it will actually make your latch. Okay, so the answer over here is in the CMOS latch and the jam latch, your what happens, your uh, the node voltage remains the static with respect to time. Okay, so this was again a very easy question. I will move to next question. You may interrupt me wherever you are actually not understanding the concept. This is a gate given over here. It is a 3-input NAND gate, which the question over here is, which input combination has highest gate leakage current, highest subthreshold current, and highest total leakage current? Okay, so which of this combination will give you all of these three? Okay, So to have highest sub-threshold leakage current and highest gate leakage current and highest total leakage current, you can have only two combination. Either all of the inputs are 0, 0, 0, or all of the inputs are 1, 1, 1. Okay, so these are the actually two scenario which can happen. Okay, here it has been given that the I gate of all the PMOS is 0, right? So gate leakage of all the PMOS is 0. Okay, so the gate leakage should happen from all the NMOS. Okay, so to happen the gate leakage for all the NMOS, right? All the NMOS should be provided by 1, 1, and 1. Okay, so in that case, what happens? It will have the highest gate leakage current. So in 111, it will have highest gate leakage current, right? Now, when you provide 111 to this, right? So the PMOS, all the PMOS will be off, right? Although the gate leakage current is 0, right? But it will actually be in the subthreshold region, and all three are being in the subthreshold region. So what it will do, it will have your highest subthreshold leakage, right? So in 111 case only, it will have higher subthreshold leakage. Now if you have highest subthreshold leakage and highest gate leakage in 111, right, so the total leakage current will also be highest at 111, right? 111 means A, B, and C. Okay, so this is how this question can be done, right? And I think in your class there was a table which has been given over there, and if you see that also, you will realize that for 111, 111, and 111, your gate leakage and subthreshold leakage and the total leakage current will be highest. Okay, so this is question number 6. I think I have a couple of more questions. This is question number 7. Okay. In this design, the question has been given over here is in the latch design, discuss which of the following statement are correct. Right. For latches, which of the following statements are correct? Anyone? So you just have to tell me the answer. Okay. So there are 5 options. 6 options we have. Which of these options are correct for the latch design? Anyone? Okay, so let me tell you the answer. Okay, so you're quite very quiet. Uh, I hope you are understanding whatever that has been taught in the class and whatever we are discussing over here. Right, the first statement is CMOS latch with output feedback and input inverter, and CMOS latch with output feedback. Okay, reintroduces output noise sensitivity. Right, so if you have a positive feedback like this, right, and if there is some output you are taking, and if there is any noise over here, it will actually be amplified in the input. Okay, so a large noise spike at the output can propagate backward through the feedback and corrupt the state, right? If there is a very large noise, right, if suppose it is 0, and if there is, it is going to say 450 millivolt or 500 millivolt above threshold voltage, the what will happen, it was earlier 1, right, and because of this noise, it can become 0. Okay, so for latches, it is because it is a positive feedback, right? If there is noise, noise can actually corrupt the gate. Okay, so that you have to keep in mind, and this statement is correct. Okay, now the question is, CMOS latch with output feedback has static output during both the state of the clock, right? That is also correct, right? Because the output is actually fixed. If it is 0 or 1 in both the state, the latch output actually remains the same, right? So the latch output doesn't changes, right? That is the reason it is latch, right? So this statement is also correct. Now the third statement is C, the clocked C square latch is opaque when phi is equal to 1, right? So that is wrong, right? It is not the case, right? The fourth statement is CMOS latch addresses all the deficiency discussed. The latch is static, all nodes swing rail to rail. The state noise is isolated from the output noise, and the input drive transistors gate rather than the diffuser. Okay, the input drive transistor gates rather than the diffusion, right? So all the four statement which has been given over here, that the latch is static, okay, then the all node switch rail to rail, matlab it means that it will go from 0 to VDD, okay, 0 to VDD or VDD to 0, right? So that is also correct. Static noise is isolated from the output noise, right? If there is if there is some static noise, actually it won't create any difference. Okay, so that is also true, and the input actually drives the transistor gates rather than the diffuser, because there are inverters which are placed, right? If there is an input, it is actually driving the gate rather than the diffuser, right? And if it is driving the gate, then there is a very less chance of noise, right? That's the reason the CMOS latch are preferred, and this statement is correct, and other two statements are actually wrong. Okay, all the latches are transparent when phi is high. Both the circuits cannot be made active low without adding extra transistors, so that is not true. And jam latch requires extra clock load. That is also not true. In the jam latch, actually we reduce the number of the transistors. Okay, so yeah, this was question number 7. Any questions? Since you are not asking question, the lecture is running very fast, right? I have actually reached the last question of today. This is the last question of today, because you are not asking question. If you can ask, if you ask questions, right, we won't run very fast, but the question is very simple. The question says that, okay, you calculate the subthreshold leakage current in the following circuit. Okay, the following circuit has ABC 101 input. The eta is 100 millivolt. Okay, uh, then the S is 100 millivolt per decade. Then the VT is also given 0.3 volt. VDD is 1 volt, right? And use the subthreshold leakage expression and find the final answer, right? It's very simple. What is the subthreshold equation? Is we have actually seen over here, right? So this is the equation, right? And if we actually write this equation over here, it will be uh, you can see it is 101, right? 101 means this is 1, this is 0, this is 1, this is 1, and this is 0. Okay, so this transistor is off, this is on. Okay, this transistor is off, this transistor is off, and this, oh, sorry, this is on. Yeah, this is also on. There are two transistors which are off, M2 and M5. Okay, because the inputs are given like that. If there are only two transistors which are off, the leakage is, whatever leakage we calculate, it is actually multiplied by 2 times, right? So this will be 2 times multiplied by I off, that is my IDS, right? And this will be actually multiplied by 10 to the power VGS plus eta VDS minus VDD. Okay, then it will be actually subtracted by k gamma of B sub, that is my the body bias voltage. Then it will be divided by subthreshold slope, SS. Okay, and if I put all the values, it will be 2 times multiplied by I of, multiplied by your 10, and this will be 100 e to the power minus 3 minus 0.3, then divided by SS is again 100 e minus 3. Then if you calculate, this will be 2 times I of, then it will be multiplied by, so if you calculate this, it will come around 0.50, right? You have to trust me on that. It will be 1.0024 multiplied by I of, right? So the final answer will be 1.0024 multiplied by I of, and this will be the answer, right? So this is actually the last question. So what we have done in today's lecture and in the last couple of lecture is we have discussed about static and dynamic power, right? And I'm just repeating again whatever I have said. Okay, so there are two kinds of component of power: the static power and the dynamic power. Okay, the dynamic power only is being consumed whenever there is a transition, right? There is a transition of input node, there is a transition of internal node, or the transition of output node. If these three things happen, right, in that case the dynamic power will be consumed. Whenever there is a transition, what happens is there is a short circuit path which is being formed between the VDD and the ground, because at the transition, right, both NMOS and PMOS are on, right? Whenever both NMOS and PMOS are on, there will be a short circuit current that will be flowing. Yeah, I will be discussing about the subthreshold leakage. Yeah, so there will be short circuit current that will be flowing, and because of that, there will be a power consumption, right? Whenever there is a current flow, right, there is a voltage, there will be power. Power equal to V into Y, right? The second is the leakage current, right? That is what we call a subthreshold current, right? And the leakage is actually of three types, right? We have seen it can be the gate drain leakage, it can be the gate dielectric leakage, and the most important component is the subthreshold leakage, right? Ideally, what is the case? Ideally, we want that our transistor is an ideal switch. Whenever your transistor is input is, so if this is an NPOS, wherever your transistor input is zero, when it is off, there should not be any current flowing. Whenever your transistor input is one, when transistor is on, right, there is the current should flow, right? So that's what our understanding is, right? So that's how your digital circuit should work. But your transistor is not an ideal switch. It is not an ideal switch. What does it mean? That when your input is zero, right, when the input is zero, still there is a current that is flowing, and we call that as subthreshold current, right? So what happens is, because of this, and why the subthreshold current is flowing, because of the minority carriers. This is not due to the majority carriers, this is because of the minority carriers, right? This current flows, and because of that, what happens? What you wanted, that okay, my device is off, right, because all the input you have provided is either 0 and 1, there is no connection between VDD and ground, right? No current is flowing. Ideally, your battery should last lifetime if you are not doing any work on your laptop or mobile, right? If you keep the laptop as it is, right, just in the idle condition, the battery should not drain. That's how our understanding is, or that's how ideally it should be. But because of this subthreshold leakage, right, despite your transistor being off, this current is flowing, you have the battery lifetime reduces, right? You might have observed that you just keep your laptop idle, it is not doing any work, still your battery will reduce. You just keep your mobile idle, right, you don't do any work, right, and just come after one day, your battery will reduce. And why it is happening? Because of the leakage, right? And what we want, that this leakage should be minimized as much as possible in the battery operated devices, right? So that's the reason this subthreshold leakage current, it becomes extremely important for us as a designer, right? Because you have to now take care of this subthreshold leakage, right? I will just give you an example. Suppose in the pacemaker which has been fitted in your heart, right, for the heart patient, right, there is a battery which is there, right? And once you fit, right, you assume that your pacemaker should actually run for say multiple of years, right? But assume that, but you see that if your transistor is very leaky, right, what will happen? The pacemaker will stop working after some time, right, because all the battery will be drained, right? In the pacemaker, you don't want that your transistor is working at 1 gigahertz, because the pacemaker beeps at our heartbeat, right, 72 beats per second, right? It can be extremely slow, but the only concern over there is the power, right? The lifetime should be as high as possible, right? There, this that the what I've said, right, the high voltage transistor or extra high voltage transistor, high threshold voltage transistors become extremely important, right? So whenever you design uh, hardware for a device like smartwatch, right, the pacemaker, or the devices which are handheld devices which are not running at very high frequency, right, which are not running at 1 gigahertz or 2 gigahertz, just like your laptop, what do you want? That there you use the transistors which are extremely low leakage, but it can be of subpar performance, right? You don't want 1 gigahertz frequency. If it is giving you 100 megahertz, it is fine. If it is giving 150 megahertz, it is fine, right? And there you use high voltage, high threshold voltage transistor, HVT transistors you use, right? But on an alternate side, suppose in the servers, right? You have continuous power supply, and there you want that your server should run at extreme high frequency at say 5 gigahertz, right? There you will be using low BT transistors. So there you are not concerned with leakage. There you are concerned that okay, if you are running a neural network, it should immediately give you the answer, right? If you're running an algorithm, if you're clicking on Google, it should immediately give you the response, right? That's how it works, right? Now everybody is using Chat GPT, right? You might, if you are using the free version, Chat GPT takes some time to respond, right? Why? Because it is going through the cloud and it is coming back, right? But if you have some hardware which can locally run Chat GPT locally, right, in a very fast manner, right? Yeah, it will be extremely fast and extremely useful for us, right? But even if the server it is going through the server, right? The servers which are running this kind of model should be extremely fast to get the response as quick as possible, right? So these are two extremes, right? So when you are talking about high performance, high frequency and everything, you talk about larger current, and there you talk about dynamic power and dynamic energy consumption, right? Because you are switching very high. But when you are talking about low power devices like handheld devices or devices which are not working at extremely high frequency, there you talk about the static power, okay? And there you try to reduce the static power as low as possible. Okay, I hope I have answered your question. If you have any more question, feel free to ask. Other students, any more question? If you have, feel free to ask. Okay, so yeah, you have to ask question, right? Otherwise, these lectures will become not not of much importance, right? So we are actually arranging this lecture such that you understand the concept in a better manner. So if you have any question, you may want to ask in the WhatsApp group. Okay, and I have actually also shared a link in the WhatsApp group, right, of the courses which you can do, right, if you want to be proficient as a good VLSI designer, right? So you just want to follow, right? If you so this is the WhatsApp group link. If you have not joined, you can just scan it or just see it. You can join. So you come back to the next session. I will try to actually cover both week 11 and week 12, right? Such that we will have three lectures. At the end, we will have three lectures where we'll be discussing more about the VLSI research which is going on, and what are the skills that is required to get into industry. And if you are in industry, how you can upgrade your skills so that you can do more complex job, right? So that will be the goal of maybe last two lectures or three lectures, right? So thank you everyone for joining this session. I will just sign off from today.